Welcome back. No, we are going to very difficult condition. And I told you in my previous video, love yourself. Because if you don't love yourself, how other people love yourself? Don't feel alone. Don't feel no one care about me. If you don't love yourself, how people will love you? And face any problem and accept the condition. Okay? In my previous video, I have discussed about automorphism. Automorphism is a foundation of group theory. Because we all of us know, homeomorphism is very important for group theory. And if you want to find number of counting homeomorphism between two groups, then if you know the automorphism of the group, then it will be so easy to find homeomorphism. At first, I will discuss one question of automorphism which has come in CSIR NET. Let's see the question. For any group G, let automorphism G denote the group of automorphism of G. Then, which of the following are true? Option 1. If G is finite, then automorphism of G is finite. Option 2. If G is cyclic, then automorphism G is cyclic. Option 3. If G is infinite, then automorphism G is infinite. And option 4. If automorphism G is isomorphic to automorphism H, where G and H are two groups, then G is isomorphic to H. At first, I will verify option 1. Option 1 is if G is finite, then automorphism G is finite. Okay? We all of us know automorphism G is the collection of all isomorphism on G. If be the member of automorphism of G imply F is mapping G to G, which is an isomorphism. Okay? At first, suppose this option not true. That means assume odd G is infinite when G is finite. Are you getting? At first, consider all function f from a to b, which is actually bigger than isomorphism because it is set of all function. Then we all of us know total number of function a from a to b will be cardinality of b to the power cardinality of a. This is total number of function, and automorphism of G is the collection of all isomorphism f from a to a. If total number of function denoted as S, automorphism of G always will be subset of S. Are you getting? And if A and B are finite, then total number of function always will be finite. And since automorphism of G subset of S, that means automorphism of G must be finite if the function is finite. Are you getting? That means option 1 is a right option. Second option is if G is cyclic, then automorphism G is cyclic. We all of us know Zn is a cyclic group. And automorphism of Zn or Zn is isomorphic to Un. We all of us know. That means Z8 always will be cyclic group. And I have seen in my previous video, U to the power n is isomorphic to Z to the power n minus 2 direct product Z2. So, automorphism of Z8 by this theorem is isomorphic to Z2 direct product Z2. And we all of us know this is not a cyclic group. Therefore, our option is a wrong option. If G is a cyclic group, then automorphism of G may not be cyclic. Okay? Now let's verify third option. Third option says if G is infinite, then automorphism G always infinite. Consider the mapping F from Z to Z, where Z is infinite. And we all of us know this is an example of isomorphism. But what is the automorphism? Automorphism always maps generator to generator. I have discussed it in my previous video. So automorphism here, f of x equal to x and f of x equal to minus x. That means automorphism of Z is isomorphic to C2. Therefore, our third option is wrong. Here, the group is infinite, but automorphism is finite. And the fourth option says, if automorphism G is isomorphic to automorphism H, where G and H are two groups, then G is isomorphic to H. Notice, automorphism Z10, which is isomorphic to U10, and by this formula, um times n equal to um times un, when GCD of mn equal to 1, we can write is um times u2. Okay? And u p to the power n is similar to z phi p to the power n, where phi is a prime number. Okay? Then it is similar to isomorphic to Z4. That similarly, automorphism Z5 is isomorphic to U5 and U5 equal to actually Z4. So notice here automorphism Z10 is equal to Z4. Similarly, automorphism Z5 is equal to Z4. But is Z10 is isomorphic to Z5? No, because here Z5, because here order different. Therefore, option 4 is a wrong option. If automorphism of G is isomorphic to automorphism of H, it does not imply G always will be isomorphic to H. Are you getting? Well, that means in this question only option 1 is correct. And this question is very important for group theory. Now I will classify the group. Let S be the such G such that order of G equal to n. That means collection of all group of order n. Then class of G1 equal to set of all G in S such that G is equivalent to G1. That means set of all G in S such that G is isomorphic to G1. And class of G2 equal to set of all G in S such that G is equivalent to G2. That means set of all G in S such that G is isomorphic to G2. Are you getting? Class of G1, class of G2? Okay. Let's consider such set such that order of G equal to 4. That means this is set of all member Z4, K4, Z2 cross Z2, cyclic subgroup generated by 1, 2, 3, 4. Set of fourth root of unity means 1, minus 1, I minus I. Set containing the element identity 1, 2, 3, 4, 1, 3, 2, 4, 1, 4, 2, 3. Okay? And other x minus x, 1 over x minus 1 over x, so on. Are you getting this group? These are all collection of order 4. Okay? Now class of Z4 equal to, we all of us know Z4 is a cyclic group. That means set of all G in S such that G is isomorphic to Z4. That means this set contains Z4 cyclic subgroup generated by 1, 2, 3, 4, set containing the element 1, minus 1, I, minus I, so on. That means which are cyclic group of order 4 and class of K4 equal to K4 Z2 direct product Z2 set containing the element x minus x 1 over x minus 1 over x, so on. That means number of group up to isomorphism of order 4 is 2. Are you getting? Well, now at first I will say fundamental theorem of finite abelian group. This is a classification theorem. This theorem tells us which group are abelian of a finite order, and this theorem is a foundation of group theory. This theorem based on some result which I have seen so far. Result number 1 is every group of order P is isomorphic to Zp. Second, if the group of order P square, then it is isomorphic to Z, either Zp square or Zp direct product Zp. And Cauchy's theorem. This theorem tells if G is a finite group and P is a prime number who is dividing the group of order G, then G has an element of order P. That means G has a cyclic subgroup of order P. And the statement of the theorem is, if G is a finite abelian group, then there exists two different representation. There exists prime number P1, P2 up to Pn. Not necessary those are distinct. And integers K1, K2 up to Kn such that G is isomorphic to Zp1 to the power K1, direct product Zp2 to the power K2 up to direct product Zpn to the power Kn. And that means every finite abelian group is isomorphic to a direct product of cyclic groups of prime order. Are you getting the statement of the theorem? And this representation is unique up to rearrangement. Actually, this theorem tells us every finite abelian group can be decomposed as a direct product of its subgroup, where those subgroups have ordered powers of prime. Then there is a nice theorem, prime power partition theorem. Let G be a finite abelian group of order prime power. Then there is a partition K1 plus K2 up to Km equal to K and cyclic subgroup G1 equal to cyclic subgroup generated by A1 of order P to the power K1, G2 equal to cyclic subgroup generated by A2 of order P to the power K2 up to Gm equal to cyclic subgroup generated by Am of order P to the power Km. Then G1 cross G2 up to Gm equal to G, which is internal direct product. That means different partition of power gives different structure of the group. Are you getting? Actually, finite abelian group talks about prime power. Without prime power, it cannot talk anything. Let's consider one example, G equal to 1008, which we can write as 2 to the power 4 times 3 squared times 7. And look, these are product of distinct prime. So, we can tell G is isomorphic to some abelian group of order 16 times direct product some abelian group of order 9 direct product some abelian group of order 7. Okay. and here 2 to the power 4. We can partition, that means p to the power k, then we can partition 4 in different way. 4, other way is 3 plus 1, another way is 2 plus 2, other 2 plus 1 plus 1, and another is 1 plus 1 plus 1 plus 1. Are you getting this partition? That means there are 5 different ways to partition 4. And 4 gives here Z4. 3 plus 1 gives here Z3 direct product Z2. 2 plus 2 gives Z4 direct product Z4. 2 plus 1 plus 1 gives Z4 direct product Z2 direct product Z2. Okay? And 1 plus 1 plus 1 gives Z2 direct product Z2 direct product Z2 direct product Z2. Are you getting? That means here 4 gives 5 option, and we can partition 3 square. Here the power 2. 2 can be written as 1 plus 1, other only 2. That means there exists 2 different way to partition 2, and it gives Z3 direct product Z3, and it gives 2 gives Z9. Okay? And here 7 to the power 1, power is 1. 1 can be partition only one way. This only gives Z7. Therefore, we can tell there exists 5 times 2 times 1 means 10 different possibility. Okay? So, for G16, there exists 1 plus 2 plus 3 plus 4 plus 5 different way to make the subgroup of order 16, which I have indicated in red color. Okay? And for G9, there exists only 2 different way, Z9 and Z3 direct product Z3, which I have indicated in blue color. And there exists only one way to make the subgroup of order 7, only this. Therefore, actually there exists 10 different way. G is isomorphic to one of these. Okay? Now let's see one more example. Groups of the form p to the power k for a prime p when p less than equal to 4. Because I have told you this theorem only tells about prime power. At first see the group of order p. Since here the power 1, so there exists only one possibility. This is Zp. Now the power order of p square, and the possible way to partition these 2 is 2, which gives Zp square, and other 1 plus 1, and which gives the group Zp direct product Zp. That means there exists 2 possible groups of order p square. Similarly, order pq, here the k is 3, then partition this 3, at first 3, then it gives Zpq, other 2 plus 1, then it gives Zp square direct product Zp, and other is 1 plus 1 plus 1, and this gives the group Zp direct product Zp direct product Zp. That means there exist 3 possible groups of order pq. Now consider p to the power 4. Here the power 4. Now partition 4. At first 4, then it gives Zp to the power 4. Other 3 plus 1, then it gives Zpq direct product Zp. Other 2 plus 2 gives Zp square direct product Zp. Other partition 2 plus 1 plus 1. This gives Zp square direct product Zp direct product Zp. And other possibility is 1 plus 1 plus 1 plus 1. and this gives ZP direct product, ZP direct product, ZP direct product, ZP. That means there exist 5 possibility of order 4. That means there exist 5 possibility of order p to the power 4. Okay? Well, now let's see the abelian group of order 16. 16 equal to the power 4. Here p equal to 2 and here the k equal to 4. So there exist 1, 2, 3, 4, 5. 5 different ways of partition to make the group of order 16. By this partition, we can take there exist 5 different abelian group. Are you getting? Now my question, is this group are isomorphic to each other? For this, at first let's see how to find the number of elements in Zm direct product Zn. Let's consider AB be any element of Zn cross Zn and such that order of AB equal to T, which is LCM of order of A and order of B. Suppose there are k combination of Ri, which is order of A, and Si, which is order of B, and whose LCM are T, then possible combination are LCM of R1, S1 equal to T, and the number of elements of order T equal to phi R1 times phi S1. Other LCM of R2 S2, which is equal to T, number of elements phi R2 times phi S2 up to LCM of RK and SK, which is equal to T, and number of elements of order T equal to phi RK times phi SK. So total number of elements of order T in Zm direct product Zn equal to summation R equal to 1 up to k phi Ri times phi Si. Okay? Are you getting the possibility? Let's see one example. Number of elements of order 5 in Z10 direct product Z15. Let's consider a arbitrary element AB in Z10 direct product Z15 such that order of AB equal to 5. Now see the divisor of 10. These are either 1 or 2 or 5 and 10. This order of element can possible in Z10, we all of us know. Then now see the divisor of 15, we all of us know these are 1, 3, 5 and 15. That means this order of element can possible in Z15. Are you getting? Now we have to show how many combination exist in Z10 direct product Z15 of order 5. That means we have to choose LCM of order of A and order of B equal to 5. If we choose from 10 1 and from 15 5, then LCM of 1 and 5 will be 5. Similarly, if you choose 5 for 10 and 1 for 15, then LCM of 5 and 1 also will be 5. If you consider both 5 from 10 and 5 from 15, then LCM of 5 and 5 also will be 5. And this is the combination of LCM for order 5. Are you getting? Now let's see the number of elements of order 5 in Z10 direct product Z15. This will be phi 1 times phi 5, which is equal to 4. For this, phi 5 times phi 1, this is also equal to 4. And for this phi 5 times phi 5, which is equal to 4 times 4, this is equal to 16. So, total number of possibility of order 5 in Z10 direct product Z15 will be 4 plus 4 plus 16. This is equal to actually 24. That means number of element of order 5 in Z10 direct product Z15 will be 24. Are you getting how to find number of element in Zm direct product Zn? Okay. Now let's come back the original question. Now I am sure my all viewers have understood how we have to find the number of elements in Zm direct product Zn. For this, there are 8 elements of order 16. If you find, then you will understand it easily. But for this, there exists no element of order 16, but there exists 8 element of order 8. And for this group, there exists no element of order 16 or 8 and 12 elements of order 4. And for this group, there exists no element of 16 or 8, but here 8 elements of order 4, here 12 elements of order 4. So this group are not isomorphic. And for this group, there is no element of order 16, 8 and 4. So this abelian group cannot isomorphic each other. Are you getting? Therefore we can tell any prime power of order cyclic group of given finite abelian group is isomorphic by looking how many elements there are of each order. Okay? Now let's see the number of group up to isomorphism of order n. When order of G equal to 1, then it will be number of group up to isomorphism only 1. This is Z1. And number of abelian group up to isomorphism also this group Z1. When n equal to 2, since 2 is prime number, this is always cyclic and this is only Z2. And number of abelian group up to isomorphism also Z2. When n equal to 3, this is also prime order. So this only Z3, which is cyclic, and abelian group also up to isomorphism Z3. And when n equal to 4, there exists two possibilities. One, Z4, which is cyclic, and other is K4. And number of abelian group up to isomorphism, one cyclic, which is also abelian, and other K4, which is abelian but not cyclic. For n equal to 5, since this is a prime number, so number of group up to isomorphism only Z5 and number of abelian group up to isomorphism only similarly Z5. When n equal to 6, then number of group also up to isomorphism 2, one Z6 which is cyclic and other S3 which is also isomorphic to Z3 which is non-abelian group. That means when the order of the group is 6, then number of group up to isomorphism is 2, but number of abelian group up to isomorphism only 1. This is Z6. When n equal to 7, this is prime number, so always will be cyclic. This is only Z7, abelian also only Z7. When n equal to 8, there exists 1 Q8, other dihedral group with order 8 mean D4, Z8, Z4 direct product Z2 and Z2 direct product Z2 direct product Z2. There is 5 non-isomorphic group of order 8 and only 3 abelian group Z8, Z4 direct product Z2 and Z2 direct product Z2. Are we getting? When n equal to 9, this is the type p square. We all of us know any group of order p square is abelian, and this is Z9 and Z3 direct product Z3. Abelian also Z9 and Z3 direct product Z3. Okay? Well, for n equal to 10, there is only two possibility, one Z10 and other D5, and abelian only Z10. Okay? For n equal to 11, since 11 is a prime number, this is only Z11 and abelian also Z11. And for n equal to 12, there exists 5 possibility. 1 D6, other A4, other Z2 semi-direct product Z4 and 2 abelian group Z12 and Z2 direct product Z6. Okay? That means abelian group are Z2, Z12 and Z2 direct product Z6. When n equal to 13, then there exists only one possibility, because 13 is a prime number. This is Z13, abelian also Z13.